So this is a fast-growing digital health startup that aggregates data, almost 127,000 active users. So they have substantial user base, and they deliver personalized wellness recommendations. So that's their business. Now they're planning to launch a predictive health risk score that insurers and employers can use to basically design their wellness programs. Now, the challenge in most of the data mining problems is that data would be messy. There will be missing values, there will be inconsistent scales, there will be variables of different types, but we are expected to utilize all of this to make sense of it. So in this case, the decision point is how do we clean, transform, and reduce that data? Because unless we do this, we will not be able to come up with accurate predictions. They could be biased. So let's open up for discussion. I'm going to show you whatever the figures are, and I want to look at your reflections on it. So here is what I mean typically would happen, that you are engaged in any company as a data mining analyst, business analyst, whatever the case might be. You will end up having a set of variables, and these variables can vary. We have talked about types of variables. They could be nominal, they could be binary, ordinal, interval, ratio, etc. So in this particular case also, you have a wide variety of variables, right? So the question is, how do we make sense of it? So if you were to be encountering something like this, clearly first question that you have to ask is, what are we going to do with this, and how do we address some of these different types of data that we have? So that would be something which I would like to open up, to see what would be your first reaction once you have this data. What would you do as a first step in your data mining exercise? Again, this is a case discussion, so it's not a lecture, one-way lecture. We will be discussing, it's a graduate class, so I'm looking forward to discussing it as a case discussion. Yeah, go ahead. I see your hand raised.
Yes, perfect. So I think in the first step it would be kind of important to get like a basic understanding of what the data actually is, how it's structured. And it says here whether it is a nominal, binary, interval, ratio, etc. Um, and then I would immediately go and continue checking for completeness and what data is complete and whether I should impute the mean or the median or um,
Yep.
if a lot of data is if a lot of data is missing, I should either impute or if it's just a like a tiny percentage, I don't know, 10%, I could consider just not using the data that is not there.
So as a
But in
first
our
step, yeah, as a first step, would you first look at completeness, or would you look at the way these variables are distributed between nominal, binary, ordinal? And that's one of the question, because we will get to the
ah,
completeness and consistency and all those things. But I was just trying to see what would be the first reaction if I were to have data like this. Am I going to first look at how many missing values I have, or am I going to see, okay, I have this distribution of different types of variables and I'm supposed to do something with it? So I just want to see the first reaction. So are you saying that you would first look at the completeness as your first reaction?
um, I would say from basic instinct, yes, but before I impute, I would check for example, the maximums and all the descriptive data, because if I choose to impute data and if I have like a very high maximum, that could negatively impact my imputation and therefore like mess with my whole analysis at the end.
Yep. Okay. Yep. Sure.
But yeah, I would check if there was some of these issues there.
Sure. Yeah. Okay. Anyone else?
I think it mentions in the case study of, I think the exact language is a data profiling. So I think what that means is getting a clear understanding of what the different variables you'll be looking at
Hmm.
and the importance for each. Importance meaning the number of variables for the number of data types or
Hmm.
different data labels for each variable.
Hmm.
So, yeah, an initial screening of the different variables would be my first step.
Okay. Now, if I see ordinal data, stress level 1 to 5, sleep quality could be poor, fair, good, excellent, or activity level, very active or not active. What do we do with those things? These are written many times. These are written in text form. So how do we utilize them? Yep. Go ahead.
Um, I would say for the ordinal data like poor, fair, good, and excellent, I would either create dummy variables
Mm.
or transform it into like a kind of scale from like the stress level from one to four in this case.
Hmm. So there will be a dummy variable. So we talked about this a little bit in the last class. So I just wanted to see, you know, whether those are things that will come in mind that, okay, we are expected to convert some of this into quantitative values. And when we create dummy variables, we have to be aware that one of those will be reference point. Um, for example, sleep quality, poor could be the reference point, and everything else will be with reference to the poor quality sleep. So that's something which, I mean, I would think of which ones are textually written and which ones I need to quantify. How do I do this? How many dummy variables will be needed in some cases? Are the missing values, coming to that, which was also mentioned, mostly in the ordinal type of data, or is it in the quantitative type of data? Those are things which will be important. I also would be interested in seeing, am I having more missing values in the dependent variable that I'm supposed to predict, or is it more on the independent variables, the ones that I'm going to use as predictors? Right? So I want to understand how exactly all this is distributed in terms of text versus quantitative, missing at random, and where exactly they are missing, which kinds of data are missing. So that's something which becomes critical. So here is something which the case has provided. They looked at the case, the data, and then they realized there are some quality issues here. Completeness, there was quite severe situation with 34% of users missing their EHR data. Right? So electronic health records data is something which they're going to use eventually, and 34% of them don't have it. 18% missing sleep data, blood pressure field 42% incomplete. So there is sort of variance across different variables. And some variables among these might be more important than the others, and having missing values there actually means more for us from predictions perspective. So that's something which obviously is connected to what we were talking about in the previous slide. So when we have this issue of completeness, um, we have to think about how do we address it. So there was some discussion about imputation. Again, the case has talked about it, different options that we have. So I would like to ask that again from the class, among the options that the case has provided, what do you think the team should do to handle the extensive missing data we have here? Which one would you choose among the options? All right, I'm looking for others also to contribute. Okay, I do want this to be a conversational, discussion based class. You all have submitted your executive briefs, so obviously you have done something with the case.
I would choose the imputation method because deleting like rows would mess with the data. So the best like way to go would be to impute the data,
And which way will you impute? There are multiple ways in which you can impute. So you won't want to drop the data, which is clear. But among the different imputation methods, there are few that are listed in the case. Which one would you prefer?
To find like the median.
To look at the median and replace with the median. Okay.
Yeah.
And why you think that would be the best approach in this case? According to your overall thinking?
Because if we use the median, we're less likely to be using like extreme values.
Okay, so you are concerned about the outliers and
the outlier.
so you would use that, and therefore the issue of outliers can be addressed. All right. Somebody else?
I would try and get rid of these extreme values or check if they make sense. For example, test if, for example, people who have a very high average daily step count also have a very high daily activity. And if these
that is
values,
going to a different question. That is about accuracy, right? We are getting into the accuracy of outliers.
yes, but I want to
I'm looking at
impute with
completeness.
the mean, and I cannot impute with the mean if I have high extreme values, which is why I took this this step first. But then I would also impute the mean, but I would use wouldn't use the mean of the whole sample, but put it into segments that kind of make sense based on other factors, like
Okay.
age groups or I would probably say age groups.
Okay. So you will segment first and then use segment-based mean, whatever the segment might be. It could be age or whatever else. Okay, that's another alternative. Okay. Less likely to be biased. That's probably one of the reasons, yeah. Anyone else?
I would choose option D, which is the predictive model. Although it may take a little bit more time and a little bit more complicated to implement, I think it's the best option for basically quote unquote guessing for the missing variables, and it gives a more accurate, holistic picture for the missing information.
Could there be a drawback in that method?
Yeah, I guess the timing of it, I think in the case study, there's 8 weeks to launch for this product, and a predictive model would take a long time to implement.
So it's a
I
time,
guess that,
there's a time
yeah.
factor there. Anything else purely from modeling perspective? In the sense, can it influence the results or create some challenges with that?
Yeah, I guess in the case study, it mentions a drawback would be that the scores would be quote unquote too perfect, so almost too realistic, and not you wouldn't have necessarily outliers that make the data perfect.
So there is that challenge that it can make the entire exercise of replacement too perfect, and then you won't they will be highly correlated now. There can also be the challenge of circular logic, which the case mentions, that you're sometimes predicting using these variables, and when you impute and replace values there, you have changed the nature of that independent variable. So it can create issues with actually predicting your dependent variable. So there is, I mean, obviously there are positives in imputing with the help of predictive model. It is more sophisticated. It is actually taking the entire distribution of the data. But there are also challenges, so we have to be aware of this when any of the exercises are being taken. So all these are fair points, segment-based mean, predictive model, median-based, all these can be different approaches, and it depends on how the data mining analyst thinks about the data and overall understands the context within which this has been done. Right? So sometimes jumping straight away to doing certain things versus thinking about these aspects become very important, and that's one of the things the objective of the case was, to highlight the bigger picture. And then you have consistency, which is weights record that are both in pounds and kilogram. Then you have height, which could be in inches and centimeters. So obviously, we have to correct that. We have to make sure that all of these are in the same unit. If it's weight, all of them should be either in pounds or kilogram. So that's sort of straightforward. We want to be consistent across all the cases. We talked a little bit about accuracy, the outliers, and we also got some feedback about what we should do to capture the accuracy, whether they are really true outliers, which actually tell us something about the data, because not every outlier is to be eliminated. Some outliers actually are helpful. It tells us how the data is distributed. There are some unique individuals, and we need to keep them into account. But sometimes they can be suspicious, like we were talking about the daily steps, whether it's an active user, active person, or a sedentary person. That will make a difference in whether to remove that outlier or not. Now we come to the scale variance. Let's talk about that a little bit. How do we address a situation like this when we have a very wide range, assuming that we've already taken care of outliers? And even after outliers, we do have a big range in our variables. What do we do about that? If you see a big range after having taken away suspicious outliers, what would be your next step? All right, I think I need to call now people so that I get some responses and some discussion going on from others as well. So maybe I'll start. Yeah. Okay, I see. Ali, you want to say something? Go ahead.
Yeah, I was gonna say, probably based also off the case study, normalization, or actually, I think z-score standardization might be even better because we're talking about outliers, and the z-score standardization really helps handles outliers better. So that might be one way. I think it was like you transform each variable, and you're like to set the mean to 0 and standard deviation to 1, and this just creates better normal distribution for each variable. So I think that might be a better option.
That could be one of the options, yes. So that specific type of normalization, standardization is specifically helpful when you have various types of variables, right? So in this case, we have heart rate as one variable, which is beats per minute, annual income, which is in dollars, steps is in steps. So each of them have different units within which they have been captured. So what you just mentioned about standardization and normalization, that's very helpful when you have various types of variables that are expected to predict something, right? So that's clearly helpful and something which we would want to do. In this case, definitely we want to do it because of the fact that we have different types of variables. But let's say we had all the variables that were all about money. Everything is, all the independent variables are in dollars, right? So for example, cost, how much we spent on advertising, how much we spent on R&D, etc. And the dependent variable is in terms of our profitability. Suppose we want to capture how much spending on advertising or R&D, etc., if affect our overall profitability. In that case, what would be other alternatives if we see a wide variance in companies' R&D expenses or companies' advertising expenses? Now we don't have a situation like we have here where we have different types of variables. All of them are in dollar terms. So in such situations, while we can still do the Z transformation and bring the mean and median, mean and standard deviation to 0 and 1, what else can be done? Kathy? Any thoughts on this? All right, I'm not hearing anything back from Kathy. Okay, let's see. Jacob.
I can't think of anything else right now. That's the only thing that I could come up with.
Okay.
Sorry, I know there's another method, like when people use like log transformation. I just don't know why and why that would be the case in this
Sure. Yeah.
in this example.
Yeah, so that's a good thought. I mean, clearly, if you cannot do Z transformation or min-max transformation, something we just talked about, the alternative would be to see what exactly is the distribution of that particular variable. So let's say we have advertising expenses and R&D expenses, and we are trying to predict how much is the profitability of a firm using these as predictors. At least we want to know what's the distribution of these costs. Right? Are they normally distributed? Are they skewed in distribution? Now, if they end up being normally distributed with whatever range they have, if it's high range that we see there, it should be okay. But if I see that it's skewed and has quite a bit of range, then I would use something like a logarithm transformation, because what logarithm transformation does is that it tries to remove that skewness and tries to make that entire data set more normal. Right? That's what the goal would be, that ideally we want to, and it also tries to sometimes reduce the overall spread of the data. So that would be one alternative. So something which we do have in the case, but I wanted to see how you would apply, what you would think about it when you apply to a given context. Right, so that's important to keep in mind when we are starting with it. Always data pre-processing is a critical step, and we have to think about these kinds of things, about distribution, about missing values, consistency, etc. Now, these were the outliers. We talked about it already, that when there are outliers, we need to look at it from those that are errors versus those that are legitimate extreme values. And that's something which the case does mention, that there could be two variables that actually can be correlated. And if that is correlated, then we can compare what exactly the daily steps is with respect to, let's say, resting heart rate or activity of the person, which brings us closer to a better understanding of these outliers. This was what I just mentioned a little while ago, that when you have differences across key variables, then what you would do is you would want to look at certain kinds of Z transformation and others. So first of all, they have high ranges, and number two, they have different units. So that's something which we would consider as normalization approaches. We just talked about that min-max or Z transformation or whatever that might be. Right, so that's another factor that we talked about here. And now coming to this one more point, which is discussed in the case study, which is principal component analysis, something we have also talked about in the data pre-processing. So what's the goal of principal component analysis? Should the team use such kinds of components, or should they take some other approach? Yuling, maybe I want to hear something from you. What exactly you think about this principal component analysis? Not hearing anything. I'm sure all of you are aware that we have some class discussion expectation in this class, and there's attendance and class discussion grades also. I'm hoping that you actually will contribute in, even if you're not having your cameras on, because this is a graduate class. I do think that this is where we should be talking about these kinds of things. And you've done this case study already. All right, Alejandro. All right, Arya.
Professor, I think PCA is the only approach which we have covered right now for the dimensionality reduction
Right.
that transform a dataset into a new dataset of uncorrelated variables. So I think that would be good.
And why do we do this? Like, what's the purpose of that?
I think when the dataset have a lot of variables and very much like correlated variables to reduce those dimensions, which would be
So,
easier for us to evaluate and analyze.
okay. And what's the disadvantage of doing this? Is there any drawback?
I think we could miss on some very important relationships.
What about interpretability of the results also? For example, I think the case mentions what happens when you see PC3 is highly significant. What does PC3 mean? In some cases, it becomes difficult to make a case for what exactly that component, principal component is. In this case, they've called it top loadings and tried to link it with that. But it could be that sometimes it's not easy to create a label for it, and that can be challenging.
All right. Yeah.
Roshan, okay. Anybody familiar with anything else that you would do with dimensionality reduction other than principal component analysis? Anything else you might think of doing? So this is where, something which we will, I just wanted to see whether you would think about just using the current variables, maybe reduce the number of variables. So we did have something which we will be talking about in multiple regression, a video that I have also posted, that there are ways in which we can reduce the number of variables that you want to use in the model. You don't have to use all the variables. Sometimes some variables are not necessarily giving you much information. So sometimes you don't have to reduce the dimension with principal component analysis type of approach. You can simply reduce the number of variables that you were thinking of using by doing certain things. We'll come to that in today's class as we get to linear regression. So just sort of giving a primer on that. So that's one of the cases that we had for today's discussion, that's relating to what we had covered in pre-processing, data pre-processing. But we are going to move forward to our discussion on performance evaluation of models, which is going to be our next topic of discussion, which emphasizes the importance of ensuring that whatever model we are using, we understand the model's performance. We understand it with respect to other options, but also with respect to the data that it's working on, how much error it has. So this would be the agenda. We'll look at the mean absolute error, root mean squared error, mean absolute percentage error, etc. There are different types of metrics that we typically use for understanding performance. Then we will also look at how do we visualize some of this performance. Can we rank order them? Sometimes just looking at a metric is not enough. We would like to see how this entire performance is visualized and can we rank order them. The idea of confusion matrix, what that means, receiver operating characteristic curves, ROC curves, what that is and how that can be helpful. And what happens when mistakes aren't equal, when some of these cases are more important in our data set compared to others. So what do we do in such situations? So there are cases like that we end up seeing in data mining in business context, and we need to be doing something different in such situations. So starting with the first point, which is what are we predicting? This is one of the reasons why when we started the discussion on the case study, it was important for us to understand the type of data we are having here, and then understanding what's our dependent variable. Is it a numerical variable? Is it a discrete variable that we're going to predict? Some probability that we're predicting. So there can be different types of things we could be predicting, right? So a numerical prediction would be when we are looking at a certain dollar amount for which the house will sell, or we are going to miss X number of units of sales volume next week or next month or whatever it might be. So here it's a quantitative prediction, numerical prediction. This will require continuous variables. The second would be discrete, which is categorical predictions where spam or not spam, it could be binary, buyer or no, not a buyer, or it could be multiple choices, right? So you could have 3 or 4 different categories within which you want to categorize people or different units in your data. So in such situations, we have a different kind of a model which requires to be done, which is categorical prediction. We will have a discussion on logistics regression, which primarily focuses on such kinds of situations and specifically in binary dependent variables. And the third is probability, which is propensity scores, which is what's the likelihood of an event occurring. For example, loan default. Sometimes there are certain kinds of scenarios that we need to be very careful about. In banks, loan default. In healthcare, it could be about a patient being detected correctly for disease. Right, so that probability and propensity score is an important one because they give us not just prediction, but they also gives us some confidence interval within which we are confident that our finding is in line with what the data is suggesting. Now, the evaluation approach for each of these will be different. So we have to keep these types of categories in mind as we go, as we start doing our data mining exploration. So it's important that we are aware of what exactly we are trying to do here. Now, here's a big aha moment that basically separates data mining from traditional statistics. We have seen some of these models earlier. I'm sure you have heard about multiple linear regression, maybe used it. But in traditional statistics, when you use it, the objective is to fit the model with the data that we have, with whatever data we are using, right? So it's basically fitting the data, fitting the model on the data that it's training on. So you look at R square and understand what is the level of variance in the dependent variable that can be predicted by the, or rather, which can be explained by the independent variables. We use the word explained in the case of statistics. Now, data mining is different in the sense that we are having 2 different sets of data. So we train our model on one set of data and then we test it on another data, which is the validation data. So here model fit is not of much use because just because it had a very good R square on training data does not mean that it will predict very well. So it's more like thinking of memorizing answers for last year's exam. That is what traditional statistics models would do. That would not mean that you can ace this year's test. Whereas what you want in data mining predictive models is that they learn general patterns, and then whatever comes in front of them, they are able to sort of make predictions rather than just memorizing what happened in the traditional data. So that's one of the reasons why we have to be aware of this difference between the types of models, and our course is about predictive models and then also other options that we might have. But data mining is more on the right hand side rather than the traditional statistics, but we use a lot of those tools that were built by statisticians. Now, before we get into any model, more sophisticated ones or simple models, like a linear regression, one thing we want to be aware of is that we will be comparing its performance with some baseline. And one baseline, which is the lowest bar that we can set for any model, is the naive benchmark, which is essentially saying that if in the training data we had a certain distribution, for example, if the average sales per customer in your training data is $200, then the naive model just predicts $200 for everyone. For any new data which will come, the naive model will say that, oh, that's what we would expect. The average sales per customer is going to be for a new unseen data. There will be no fancy features here, no complex algorithms, just everyone gets that average. Now, clearly that's an incorrect prediction for most of the people, but that would be sort of our benchmark. Now, if the sophisticated model that we are running cannot even beat that benchmark, clearly it is not helpful at all, right? So we have wasted all the time, all the resources in creating a model that doesn't even predict as good as the average model is. And we'll see later on that there are several times that naive model could be doing quite close to what we might see from a sophisticated model. And the question is, do we still want to use that sophisticated model? Sometimes the answer could be yes, because of some specific context within which we are using that model. So it's an important point to keep in mind. And this has happened many times. I've seen this happen so many times than you would think. Someone builds an elaborate neural network model and it performs worse than just predicting the mean. Right? So it's always important to check against the naive benchmark. Now, how do we check whether the model is good? There has to be some metrics for prediction accuracy. So these are some of the metrics for evaluating numerical predictions, mean absolute error. There are formulas of all this in your readings. So I'm not showing all those formulas, but they are quite straightforward, adding all the errors, that would be mean error, adding all of them and dividing it by the total numbers. Whereas mean absolute error would be taking the absolute value first of the error and then adding them and dividing by the total number. Right? Actual minus predicted is your error. So the mean absolute error is quite straightforward. How far off are we from on average? Take that absolute value and then divide by n. This way we can say something like on average our prediction are off by $250, for example. Mean error is different from mean absolute error because it does not take absolute value. What happens is positive error and negative error can cancel out each other. And sometimes it's an important information that we want to have. We want to keep an understanding of the sign of that error. Is it positive or negative? And then that way we can determine whether we are over predicting or under predicting. Right? So in sales forecast, for example, if we're consistently getting positive values or negative values for mean error, then we have some understanding that we are over predicting or under predicting, which is something which we want to avoid. That's called bias. So sometimes we want to capture the bias, and that's what mean error does. Now, root mean squared error, it's a very popular metric as well. What it does is it squares the error. So whatever the error is, which is actual minus predicted, it takes the square of it. Now, whenever you take square of things, if it's a large value, the square of that will be very, very large. So it basically penalizes big mistakes more heavily. If there is large error because of squaring, it penalizes such large errors more. And sometimes we want that. So a model with one massive error will have a worse RMSE than one with several small errors. Right? So that's something which sometimes we want to account for in certain types of data. Then mean absolute percentage error and mean percentage error. So mean percentage error is basically mean error, but this time we are taking not just the error, but we are dividing it by the true value so that we convert that into a percentage form, which is easy to explain to business managers. This much percentage error. And mean absolute percentage error is similar to mean absolute error, except that we are now taking a percentage using that absolute value. Again, very helpful when communicating with business leaders. Right? So these are all different types of metrics. These are all sensitive to outliers. Therefore, as we discussed earlier in the case study, we always want to visualize the errors. We want to understand whether there are outliers. There are different ways in which we can do this. And that's something which is an important initial step before we run any model. Now, I mentioned earlier that in predicting, we always have data split into training subset and validation subset. Validation is also called testing subset. And it's important that we don't overfit our model on the training data, because it's quite easy to overfit on a training data, because that's what the model is learning from. And therefore, whenever we are looking at the metrics that we just talked about, whether RMSE or mean absolute error or whatever else, we want to look at the performance of our model on both training set and validation set. Always want to look at both of them. And we don't want to see a situation where the results look very good for training and not so good for validation. They ideally should be pretty close to each other. When that happens, we know that the model is not overfitting on the training data, and it's a healthy model, right? So that's something which can be helpful. Now, along with these metrics that we just talked about, as I mentioned earlier, sometimes you want to visualize and prioritize, rank order the types of variables or types of cases that we want to focus on. And that's where lift and gains chart come into play, right? These are ranking based, not just classifying the data, but also rank ordering them in terms of which ones matter more, right? So this is more important in many business contexts. These are your best friend when you're in a situation when you can't take action on everyone, because there's always resource constraint. You cannot spend enormous amount of money on different types of customers, so you have to focus on certain customers, or you can only personally call your top prospects. In that case, you'll decide which prospects you want to call as a sales call. So this is the question that you typically answer with lift or gain chart, which is, if I can only act on a subset of data, then which subset should I pick? Lift charts will give you the answer, right? So that's something which we'll see soon. So cumulative gains chart. So there are two different charts that we'll talk about. One is the cumulative gains chart. The other is the lift chart, which is also called decile lift chart. What cumulative gains chart does is, it's basically finding the cream of the crop. So let's say first you will sort all your records by predicted probability, right? So sorted by predicted probability, highest probability at the top. Then you walk down the sorted list and count how many actual positives you've encountered. So that's on the x-axis, and then the y-axis is the cumulative percentage of target, total percentage of how many did we actually predict correctly. Now, as I said earlier, there's always a naive forecast or naive model, which basically is the simplest model. In this case, that is the diagonal, this dotted line. What this dotted line or dashed line is showing is essentially your reference, that what would happen if I would have just picked my customers at random, rather than focusing on which are my more profitable customers. I just choose them at random. What exactly would my cumulative gains look like? So it's going to be a 50. It's basically going to be a diagonal line right here. And what we want from our cumulative gains chart is that it has to be above the diagonal line, and it has to be as far away from the diagonal line. So the closer it is getting to the y-axis, the better it is. So if I had a curve like what you see here, and another curve which goes even further closer to this and then goes like that, the second one would be actually a better model, right? So we can compare model. The bigger the gap between the model's outcome that we see here versus that dashed line, the better it is model wise. So in business terms, basically what that would tell us is that I could look at the x-axis and say, okay, I choose the first 5 records, and first 5 records is going to give me cumulative gains of this much. So more than the random pick. Random pick only gives me 50%, but I can go further than that and reach here. So that's what I could do. Jacob.
How do you get the random line? Like, is it always going to be diagonal,
Always
or
a
is it
diagonal.
different?
Yeah, the diagonal is always 0.5, 50% chance that you will choose one or the other. So it's always a diagonal.
Okay.
Yeah. All right. Any other question at this stage? So the goal is create a model that can have a bigger gap between the diagonal and whatever the curve that you get from your model. Now, how do we create this cumulative gains chart? There is a Python program that is provided in your reading. There is also a video that has been posted to show you how exactly that model works. So you need to go over that to really, do it once yourself. The data is also provided. So just go through the entire process of running that model yourself, and you'll get to understand how this works. And you'll also have this assignment that asks you to actually create these charts now this week. The other type of model along with cumulative gains chart is the decile lift chart. What it does, it's a decile, which means that basically the data is divided into 10 equal parts, 10%, 20%. So every 10%, you're breaking the data into 10 buckets. And what we would do here is look at the first bar. This is the 10th percentile, 20th percentile. So if I use the first 10th percentile of my data, how much better I can do compared to a random pick. So this one, unlike the previous one where you have a diagonal and you're trying to see the spread between the diagonal and your curve, here we want to see how much more impact can I have if I were to use a model that I've created and look at the decile chart to see what's the top 10th percentile if I choose based on the model going to give us compared to if I had chosen it on random at random, right? So if I look at this first graph, first particular bar here, on the y-axis, suppose it indicates that it's lift of 2, because this y-axis right now should have numbers like 1, 2, etc. So if it's at 2 here, or 1.5 or 1.4, whatever that number is, if it was 2, it would basically mean that the top 10% yields twice the response versus randomly picking 10% of your customers. So if you choose the model and create a model and choose these customers based on the model prediction, the top 10% of them, the likelihood of those will be responding to you will be 2 times higher than had you chosen on a random basis. So the business translation would be that if your marketing budget only allows you to contact 10% of your customer base, then use this model to pick which 10%, because you are likely to have a two times higher positive outcome from yours. So you'll get double the response rate compared to random selection. And that's where the real money is, right? That's why data scientists are getting paid, because you can tell which customers you should target. So always notice how far right you can go while still beating random. So if we see that these 4 are still higher than 1 is basically equal to random, you can go as much as 40% in this case. Even the top 40% has a lift of around 1.5, so about 50% more than random. So still a lot of room to scale up the campaign while outperforming the random outcome. So something which companies would be using. So this is another model that also you have a code that shows you how exactly you can do it for a sample data that we have used in the reading. Right, so that's sort of some of the performance measures, as well as some visualization and capturing the rank orders for our outcome. Now, classification metrics, we could look at it from confusion matrix perspective. It's basically the world of yes and no, right? As compared to predictive situations like we had previously, where we're predicting, let's say, the sales volume of a company or the sales price of a TV, whatever it might be. In classification, we are in the world of yes and no, or buyer or no buyer, non-buyer, spam, not spam type of situation. And what we will do in this case is our metric would be more like a confusion matrix. It's our central tool. And it's called confusion not because it confuses us, but because it shows where the model gets confused. What exactly are the places where the model is not able to capture this correctly. So we look at this in an example. So the naive rule, it's always bet on the most common outcome. As I mentioned earlier, that let's take the scenario that there are 70% of your customers who renew their subscription for a certain streaming service or a magazine or whatever it might be. The naive rule would say that predict everyone will renew in the validation set, which means that 70% of the time you'll be accurate, right? Because your training data is indicating that 70% of your customers do renew. So without any effort, you will be correct for 70% of the time. Now here's the catch: you'd miss every single churner if suppose you have certain customers who are churning from your subscription service or magazine subscriptions or whatever. When you do this type of analysis, like I just said, randomly thinking about it, or using the data from the past and just scaling it all the way to the validation data, you'll miss every single churner. But if your job is to really prevent these churns, then that 70% accuracy is actually 0% useful. But it doesn't help us understand which were these customers that are actually going to churn, which we need to be focusing more on. We need to do something special with them. We need to send them some targeted promotions, etc. Because by doing the 70% sort of overall spread, we would not be able to identify a single person and therefore not save any money. So this is why a raw accuracy can be misleading, right? We cannot just look at the raw accuracy of our model like 70%. A model that's 99% accurate may sound very amazing, but once we realize that we are not predicting any of these churners, or we are not predicting anyone who is a fraud, let's say in the bank case, then it is not helping us, because it's something which will be scenarios that we will experience, that very small percentage of people are in the fraud category, or small percentage of people are in a certain disease category, and we really want to know who they are. So therefore we need to be using certain models. So always compare to the naive benchmark first, but then ask yourself, is my model actually learning something useful, or just parroting the base rate? Do we need to do some learning from what we have here? So that's where the confusion matrix comes. So this is a ground zero for understanding classification performance. So essentially what you see here is predicted values, predicted as non-buyer and predicted as buyer. And this is the actual non-buyer and actual buyer. We ideally would want our model to predict the actual correctly. So these greens are the ones where a non-buyer is correctly predicted as non-buyer. So 3,120, these are true negatives, truly non-buyers. And these 180 are true positives, truly buyers, right? So predicted buyer, they were actually buyers. So these two are correct predictions, true negative and true positive, whereas these two are incorrect predictions. An actual non-buyer has been predicted as buyer in 40 cases. An actual buyer has been predicted as non-buyer in 60 cases. So those are the 100 errors that we had. So if I were to look at the error rate, the total number of values here is 3,400. So my error rate is 60 plus 40 divided by 3,400, so 2.94%. Whereas accuracy is the sum of these two divided by 3,400. Right, so this 97% looks good, not too bad. But the critical insight here is that 97% hides some important details. Now, what if these 60 false negatives were your most profitable customers? They were actually buyers, but you ended up predicting them as non-buyers. But these buyers actually were giving you most profitability for whatever reason, like they were buying products that were more premium or something like that. Now, in this case, we have missed out on all of them, and still with 97% accuracy, we might think the model is great, and yet it's not all that great when we compare with what we are losing out here. Right. So, and other way to think of is, what if targeting these 40 false positives costs us money? Here we are thinking that these non-buyers, actual non-buyers, are actually buyers, and we end up targeting them with promotional schemes, and there's a cost involved in targeting. So that money that is spent is a resource spent without much benefit. So what if that amount is quite high? In such situations also, we need to be aware of this. This is why we need to go beyond just accuracy. Cannot just look at that 97%, but we have to look at other things like sensitivity, specificity. There are the cost-weighted metrics. So there are all different types of metrics that are important. But confusion matrix is a good starting point. It's a good starting point, but not the finish line. You need to go further than this. So here's where it gets interesting. We look at the cutoff decisions. Many times we have to decide, in many classification models, we don't just say it's a buyer or non-buyer, right? We give them a certain probability that is 75% likely to buy. So the cutoff that we will be using in our models will determine how we translate that probability into some prediction. Now, you'll see in the Python program that we have that we start with 0.5 because that's the default. Default is 0.5. Anything above 50%, let's predict that as buyer. Anything less than 50%, let's predict that particular person as a non-buyer, for example. Right? So that's simple, intuitive. But what if you really don't want to miss potential buyers, like we just talked about in the previous case, if they are highly profitable buyers? Then what we will do is we will lower the cutoff. We'll go from 0.5 to, let's say, 0.25. We'll cast a wider net so that we don't miss out any buyer. The drawback of this is that we will end up spending more money because we are now thinking many more buyers exist. Some of them may not be buyers. So this is something which will create more false positives, something we need to be aware of. Or maybe we only want to target highly confident predictions, right? We only want to consider those buyers who really are buyers. We don't have enough money to spend on these potential targets. So then in that case, we would want to make sure that we increase that probability threshold from 0.5 to something like 0.75. We're becoming more selective in deciding which ones our buyers are. So that's sort of the approach that we typically take. It's a business decision, not a statistical decision. So it depends on the context in which you're working. And that's what the second case will illustrate, because the second case was meant to emphasize this idea that eventually that is what we want to be able to utilize here. The context to decide which cutoff we want to consider. Right, now coming to sensitivity and specificity that I mentioned a little while ago that are important. So when one class matters more than the other, we need these metrics. When fraud versus non-fraud, one category is more important for us to really detect, or a patient who has a certain disease versus those who don't. It's more important to understand one class, and that's more important as a class itself. Then we need these metrics. Sensitivity, it's also called recall. And what it answers is, of all the actual positives, how many did we really catch? Right? Of all the positives, how many did we actually catch? In our churn example, for example, of everyone who actually churned as a customer who churned, what percentage did our model flag? Because we don't want any of those to churn. We want to target some promotion to them. So how many did we actually flag? That's what sensitivity will tell us. Specificity answers the opposite. What it does is, of all the actual negatives, how many did we correctly identify as negatives? Right? So in other words, of loyal customers, how many did we correctly leave alone, not just go after them and send them promotions when they are already loyal? How many did we leave alone? That's specificity. Now, the painful truth is that there is always a trade-off. Tuning your model to catch more churners often means there will be more false alarms on loyal customers. Right? So if it's more sensitive, then the specificity will go down. It's like a smoke detector, actually. You can make it super sensitive, so it catches every hint of smoke, but then it goes off even when you are just making a toast. Right? So that's something which we have observed. Now, what matters more depends on context. Sensitivity or specificity, which one is more important? It completely depends on the context. You would want high sensitivity, which means you would want to catch every potential case, even if some are false alarms in certain situations, like in the case of fraud I mentioned earlier. So high specificity, on the other hand, would be you'd rather let some of these go unchecked. So for example, in medical screening, it would be more like having high sensitivity because you want to ensure every potential case is properly examined. Whereas in the case of spam filtering, you will end up having some spams coming into your inbox. It's because it's by design, because you want high specificity. You rather let some spam go through so that you don't accidentally block some of your important emails. Right? So depending on the context, you would choose one versus the other. Now, the ROC curve is the receiver operating characteristic curve, very important and elegant tool in classification evaluation. So on the y-axis, we will have sensitivity, the true positive rate, and on the x-axis, we will have 1 minus the specificity, which is the false positive rate, right? So that's the two dimensions that it always uses. The diagonal line is what the random classifier would produce. So that's just like we had seen earlier in confusion in our cumulative gains chart also. So this is the random classifier would be at the 50% point here as a diagonal, basically a coin flip. Now, as you move along the diagonal, you're just trading one type of error with the other. There's no gain here. So as we go here, we are increasing the false positive rate and the other one. So that's something which doesn't give us any benefit. A good model curve in this case, if you're running a model for classification and we want to understand how well it's doing, is going to consider how this curve is compared to the diagonal line, similar to the cumulative gains chart. We want this curve to be going basically getting closer and closer to the y-axis. It should be hugging the y-axis. The closer it is to the y-axis, the better the model is. And a metric that we use is area under the curve, so which is the area between this curved line and below that. It keeps on increasing as these curves get closer to the y-axis, right? So it summarizes into a single number how good the model is. And AUC of 0.5 would mean that your model is no better than random, because that would be basically this diagonal line. And AUC of 1.0 means perfect classification, that would be actually coinciding with the y-axis. So 100% everything is under that curve. In practice, anything above 0.8 is pretty good, and above 0.9 is excellent, right? So we want to see these AUC curves to be close to 0.9, so that it gives us good classification results. Now, what's great about AUC is that it evaluates the model's ranking ability across all possible cutoffs. Right? So we can actually look at 0.5 cutoff, 0.25, 0.75, all those cutoffs that we just talked about. So it's a comprehensive score that doesn't depend on choosing a specific threshold. So that's one good thing about AUC, that those thresholds don't have to be specifically highlighted here. Now, moving to cost-sensitive learning, this is basically where everything comes together in the real-world business impact. What cost-sensitive learning does is it recognizes a fundamental truth that different mistakes actually have different consequences. Missing $1 million opportunity is very different from wasting a few cents on postage. And that's, for example, when you're trying to target some of the customers who might give you $1 million sale. But for that, you have to reach out to them through some promotional schemes, which can cost you a certain amount. So this is what it's trying to highlight. So how we incorporate this cost into an evaluation framework, this is where we are going. A concrete example will help us understand this. So let's imagine that we are promoting premium smart TVs. That's our context that we also have in our reading. Now, missing someone who would have bought costs us a certain amount, let's say $1,000 sale. And so missing a real buyer is lost sale opportunity of $1,000. On the other hand, sending a promotional mailer to this person will cost us about 10 cents. An email, for example, in some sense, there's a cost attached to it. So there's a 10,000x difference between the two. Now let's imagine two models. Both have 95% accuracy. But model A's 95 and the model A's 5% errors are mostly the missed buyers, right? So model A also has 95% accuracy, but it's missing in the 5% error most of the buyers in it. Whereas model B's 5% errors are mostly wasted promos. So there, all those 5% errors are about the promotions that we would have avoided. Which one would you rather have? Which kind of model would you have? Obviously, it will be model B, because in model B, what we are losing is just some sense on the email, but we are at least capturing all the potential customers. Model A, on the other hand, is losing us customers, potential buyers. And the business impact of these two models are quite different, even though if you look at it from purely accuracy point of view, both would be 95% accurate. So this is why pure accuracy can be misleading. We cannot just look at pure accuracy. When errors have different costs, we need to weight them appropriately. A model that minimizes, for example, total cost might have lower raw accuracy, but it will deliver better business outcome. So we have to always ask, what does each type of error cost us? And based on that answer, we will build our model and decide which model we should be considering. So that's something which we have to be familiar with as an idea. So this is also discussed in the reading in more elaborate form. I'm going to quickly go over it just to highlight what exactly it is. We also have that as a case discussion later. So the misclassification cost, as I mentioned, can differ between types of customers we are misclassifying. The cost of making misclassification error may be higher for one class than the other. The 10,000x situation that we just saw in the promo example. In other way, if you look at it, the benefit of making a correct classification may be higher for one class than the other. So this example basically says that, let's say we send a sales offer to 1,000 people. These are the 1,000 people, where on average 1% of them are going to respond, and 0 indicates non-response, 1 indicates response. So 1% of them are going to respond to this mailer. Naive rule would say that classify everyone as non-respondent. We'll still have an error rate of 1% because we know on average 99%, 1% of them are responding. So we will know that the error rate is 1, which seems seemingly good. But using data mining, we can correctly classify which ones are the right ones, right? So for example, here, let's say the 0 and 1 indicate non-response and response. So those who are non-respondents actually, and we predicted them as non-respondents, there were 970 of them. Those who are responders, and we predicted them as non-responders, there were 2 of them. And then those we predicted as responders ended up being responders are 8 of them. And then 20 are those we predicted as responders, and they were actually non-responders. So the error rate in this case is 2.2%, right? So because 2 plus 20 are the errors out of the total. So that's 2.2%, which is higher than what we would have gotten had we gone with this naive forecast, because naive approach would have just chosen this average value that we already know, that only 1% people anyway respond. So we will assume that 1% is the response rate. But here we know with our targeted model, we actually ended up having a higher error than the naive rate. But is it then a bad model or a good model is a question that comes into play. So this is what I want to ask you also. What do you think based on this discussion, whether this model actually ends up being a better model or not so good model? Error is higher here. Twice the naive model, right? So 1% versus 2.2%. How would you think about this if you were to capture the benefit of this model? You'll put some cost, like we have in the case study, there will be some cost in reaching out to those that we predicted as actually buyers. And we will also look at what the revenue we will get, right? So that's, let's say we get a profit of one from every responder as $10 to make this simpler. And the cost of sending any sales offer is, let's say, $1. There's a cost involved in sending these offers, and there's a profit from these ones. Now, under the naive rule, when we classified everybody as non-responder, so we won't send any offers, right? So there's no cost, no profit. Nothing lost here, but nothing gained either. On the other hand, if we were to use data mining predictions, what would happen is we go back to this model and we'll see that in the data mining model, we are predicting these 28 of them as our potential buyers. Now we know that 20 of them were incorrectly predicted as buyers, right? Because we predicted them as buyers, but actually they are non-buyers. 8 of them are correctly identified as buyers when they actually are buyers as well. So 28 of them we will reach out to. Now when we reach out to them, what would happen? We will spend money on them in terms of the sales offer that we are going to provide to them. 8 of them will respond, will get profit from these 8. So there's a profit of $10 each. So $80 will be the profit. And 20 of them will not respond. We are spending $1 each. So we end up spending $20 on these, right? So $80 from these 8 people and $20 spent on these with no advantage. So overall, there is a positive outcome, a net profit of $60. So that's sort of what we can end up having here with a 2.2% error in our model compared to a 1% error in naive rule. Even though the error rate is less in naive rule, it is not giving us any benefit. No cost, no profit. Here, actually, a profit of $60. So that's how we need to interpret or use these models and understand how exactly one model could be beneficial versus the other. So purely looking at it from just the error rate may not be the right way to think about this. Now, the average misclassification cost is something which we've discussed in the reading. It's basically what it does is we want to understand the optimal selection based on which type of case is more important: churner versus non-churner, buyer versus non-buyer, patient versus not a patient. Some of these are more important than others. So this model might look a little complicated, but you'll see that in the end, what matters is simply a ratio. The ratio Q2 divided by Q1, where Q2 is the cost of missing the customer class, and Q1 is the cost of missing that, and Q2 is the cost of false alarm. Right? So it's basically, assume this one is your emailing cost or mailing cost, and this is the lost revenue. You don't want to lose that. Now, in many companies, they would not know exactly what those dollar amounts are. So they would not know exactly how much is the dollar amount that we will lose if we were not to approach these customers, but they would know how important it is to identify customers versus non-customers in terms of some ratio. It's 5 times, customers are 5 times more important than, churners are 5 times more important to be identified than having not identified the non-churners. So something like that, the marketing department is typically aware of. So what would happen in such situations is you would ask these people, the business managers, what exactly they think about missing a churner in terms of how worse it is compared to a false alarm. If they say, let's say it's 250 times worse than a false alarm, it basically captures that ratio of Q2 divided by Q1. So in our average misclassification situations, we typically rely on this ratio, which is enough to tune our models appropriately. And that's something which many software tools are just asking for, this ratio. So the company has to tell the model what exactly is the ratio, or how much worse it is going to be if you miss a buyer as against approaching a non-buyer with certain promotional scheme. And then that input then helps us understand which kind of model will come out. Right, so that's something which becomes important in certain situations when we have misclassifications that have disproportionate costs depending on the type of category that we have here. Now, one more important topic, that is what happens when one class is super rare. Right? It's always possible that you have a data set in which number of people who committed fraud are way less than those who did not commit fraud in a banking data, or those customers who churn are lesser than those who did not churn. So there are some use cases where there can be some rare events, and what we'll have to do in such situations is we'll have to do something extra than just running a simple model using the training set and testing data that we just talked about. Let's say if only 2% of our customers convert into sales, a random sample, if we do that, it might barely include any converters. Right? We would not be able to get any of these. Your model has almost no positive example to learn from, because from the training data, we only have 2% of those who actually converted. So if we are going to train the model using that data, we don't have sufficient data for those converters to learn from. So what we do in such situations is we oversample. the training sample, what we do is we deliberately include more of the rare cases compared to what the actual data might have. So either sample them more frequently or duplicate them to balance things out, so that in our training data we have enough customers who actually convert and those customers who did not convert. It should not be a 98 and 2% type of a ratio. So that's what then helps us, this oversampling then helps us learn what type of customers actually convert. But then after we have done this, when you have trained the model with this oversample data, now you're going to run it with the validation data. The validation data should not be oversampled. So you must not evaluate your model on oversampled validation data. You should train that on oversampled training data. But the validation should be normal sample data. And then you try to see how well the model has predicted. If it is not possible to ensure that you don't have a normal type of data in validation, you can also have another approach, which is you correct for some of the weights that you added earlier in the model. Because you are oversampling, you can reduce that weight in the validation data. So that's something which we will talk about a little bit. So that's another case that we will end up seeing. Right? In ranking performance, typically our goal is for detecting among set of new records what's most likely to belong to a certain class of interest. Whether it's defaulters, it could be churners, whatever it might be. Now we could use lift charts, lift curves, gain charts, gain curves for binary outcomes. We just talked about that. And we also talked about this case that when the class is rare, we would want to oversample them, right? So we want to see that situation also. So the goal would be basically to ensure that the rank ordering among the records is based on the class membership propensity that we have here. Again, coming from your reading, this is a program that also exists in your reading, and there's a video that shows you how it is done. So when you are creating a lift chart, you sort by propensity. You sort the data by propensity in decreasing order of belonging to an important class, like a fraud or a churner. And then each row you compute the cumulative number of the class membership. So this is the way it works. Basically, your propensity of somebody being in that class is put in a descending order. And then you see what actually the class was. And there are two possibilities, 0 or 1. 1 is a churner, for example, and 0 is not a churner. So the first one, the model predicts a churner and it's actually a churner. So cumulative actual is 1. Second one also it predicts as churner and actually it's also 1. So you keep on adding this cumulative value. When it becomes 0, you'll notice that it remains 7. Right? So you keep adding until it's 7, but after this, 7 is added by 0. It remains 7, and so on and so forth. So this particular column is cumulative. This is the actual. And using that number of records and cumulative gains, you are basically creating those cumulative gains chart and lift charts, decile lift chart that we just talked about earlier. And when we do that, that way we are now able to understand if our model is actually doing better than the random distribution, which is the diagonal line here, and how much benefit we can get if we capture the first 10th percentile, 20th percentile. Until when do we get the benefits? So that's twice the random selection. So it tells us, the rank ordering of our cases, how we can determine that with the lift model. Now, sometimes you have multiple classes, right? Not just binary churner versus non-churner. We could have premium subscribers versus mid-range subscribers versus economy subscribers, for example. So in such cases, we can still do everything that we talked about, the confusion matrix, all those things still apply, but they just become a little more complex because instead of having 2 by 2, like we had in the confusion matrix, now we'll have m rows and m columns, right? So it will be a more complex matrix with m multiplied by m minus 1 misclassification costs. So it can be done, and there are technology available to do this. In typical decision-making contexts, such complexity rarely exists. They normally try to simplify situations. One class is typically always more important, primary class of interest, and hence there are ways to work around such complexities and make it be beneficial for the company. So that's something which is a topic that has been discussed in the reading, but we don't have necessarily any model that uses multiple classes from Python perspective, because most of the times we will have a two-class situation, which becomes important. There are a few slides that I have here, which also basically are capturing what we have in the reading, whether it is about the costs and benefits that we can incorporate using gains and lift chart. It's just a sequence of steps that we take. I've already talked about this. The reference line is the straight line in the diagonal, and you're sorting the records. So I'm not going to belabor this in terms of what we did. And the y-axis tells us how much the impact we can get by choosing the top 10 percentile, 20 percentile, and all that. So there is the cost and benefit advantage that these charts actually provide in business sense. And that is what actually the second case also highlights, that there are at certain point in time we want to decide which model is correct, and sometimes not just the accuracy, but which model will help us reduce the cost but increase the benefit. So that's what we typically look at it from, the cost involved and how much is the revenue that we can get. So cost of mailing to people at a certain amount. This is an example just to illustrate the point. And value of responder is, let's say, $25. Our response rate is 2%. What we'll see is that there will be a certain point in time after which it's not beneficial to approach customers. So there is that number that we need to be aware of. So the mailing 3,000 people results in the most profit, and after that it starts to decrease. Right? So we start to see not much benefit, but costs start to increase. So there's an optimal point in always every scenario, and Lyft can capture that. Where exactly that number goes down is when the lift actually goes below that one that we were talking about. Sometimes the lift can also go negative, as you can see, because if you end up keep on spending money on reaching out to the potential customers, you're spending on mailers and others, promotional schemes, you're not getting the outcome from that. So that's another thing which companies have to be aware of and consider models accordingly. Okay, so we talked about quite a few things. I just wanted to pause to see if you have any questions at this point. All right, moving on to the point that I was mentioning about oversampling and how we will address that oversample in the validation data. Because remember that in the rare cases, we want to ensure that in the training set we oversample, and then later on we change that in the validation set. So we'll take an example to highlight how this works. So in this graph that we will see in the following slides, we will see an optimal classification. 3 scenarios are shown. First, we will assume that there is equal costs of misclassification. So it does not matter. Second, we will assume that misclassifying a certain class, which is denoted by O's, is 5 times the cost of misclassifying class, which is denoted by X. So certain class is more important than the other class. And the third will be oversampling scheme. How do we oversample with data mining methods to incorporate such asymmetric costs? Because clearly identifying fraudsters or identifying churners is more important than non-churners or non-frauds. So this is what the illustration is going to be here. So scenario 1 is classification equal cost. So let's say we have a model. What it did is it classified this set into this class, which is denoted as O, and it classified all these cases as a class X, right? So this is something which essentially has one of these O's incorrectly classified as X. Now this is equal cost, so that's something which does not matter. But if it was unequal cost, if this O is 5 times more important to really classify correctly, then we have ended up incurring quite a bit of expense here, and we have lost by using this particular model, which has classified them by using this kind of a distribution between the two classes. So there will be another approach that would be, suppose we classify them with a different model where they are unequal cost, and because we incorporate that in the model and specify that these O's have 5 times the cost of X, this model, what it does is it classifies them in this way. Now we'll have more inaccuracy because now we have 2 of these X's classified as O's. All these are X, which is fine, but all the O's have been correctly classified, which is what the objective in this model is, because we know that these O's are more important, so we don't want to miss out on them. So we are erring on the side of more inaccuracy, but ensuring that O's don't get missed out, right? So that's something which we want to achieve. Now, to ensure that this is the case, especially in the case when we have some rare values for these O's in our training set, we oversample these O's, because as you can see here also, 1, 2, 3, 4, 5, 6 X's and only 2 O's. So there is relatively rarer O's, but in larger data set, it could be even less than that. So in training set, sometimes we oversample O's. So we put some artificial O's, add more O's by looking at the distribution of O's, or create a sample in such a way that we have more O's in it. And then that way, when we run the model, we would classify like this, like the way we did in the previous slide. But it incorporates the asymmetric cost, but we have also oversampled O's to ensure that they are included there. Now, all this has been done in the training set. Again, I emphasize the point that oversampling is done in the training set for the model to learn. But then we have to adjust this oversampling in the validation set when we are predicting something, right? So we have to adjust it. We can do different things. One is score the model to a validation set that has been selected without oversampling. So our validation set does not have any oversampling. So we could just run this model on that validation set. So that way we are accounting for oversampling and adjusting for it in the validation set. The other approach would be to score the model to an oversampled validation set, but then reweight the results. So we will take an example here to see how that works. So when we classify data with very low response rates, practitioners typically would have 50% responders and 50% non-responders in the training models, and then the validation will be with some unweighted samples. That we will take an example here. So here is, for instance, how we adjust the confusion matrix for oversampling, especially with the reweighting in the validation set. Suppose there are 20% responders in the whole data and 50% in the sample. Right? So we have consciously ensured that our training sample has been oversampled, even though the entire data has 22% responders only, but in our training set, we had ensured 50% responders and 50% non-responders. So each responder in the whole data would actually be worth 25 responders in the sample, 50% versus 2%. So this, every responder that we have in the entire data set will be equal to about 25 responders in the sample because of this oversampling that we have done purposefully. And for each non-responder in the whole data set will be worth 0.5102 of non-responders, because non-responders in the total data set is 98, but in our training data set is 50% each. So 50 divided by 98 is giving you 0.5102. So that's sort of a weight that we are capturing. What is the worth of every responder in the total data compared to the training data? And what is the worth of non-responders in the total data set compared to the training data? So these two values become important. The 25, that is for the weight that we want to use for responders, and 0.5102 for the non-responders. Now, this is the confusion matrix for the oversampled data in the validation set. So we had trained it using oversampled data, and the validation set also happens to be oversampled. We don't have a random sample where only 98% of them are non-responders and 2% are responders, but we have an oversampled validation set. So what we could do is we could use this oversampled validation set for which we create a confusion matrix, and we know what the confusion matrix looks like. We've already talked about this, but we cannot interpret the confusion matrix with these values by itself. We have the confusion matrix, but this confusion matrix will need to be reweighted, and that's the reweighting process that we are doing here. So what we do, as you can see here, is we are adjusting it based on these two weights that we just identified, right? So that 390 was for the predicted non-responders who are actual non-responders, but we know that the non-responders weight is 0.5102. So we are going to divide that 390. We are going to inflate that value a little bit because this was reduced value since we had made it 50% each. So we are inflating that by dividing 390 by 0.5102, which makes it 764. Similarly, this one again is an actual non-responder. We predicted it as a responder, but this is based on a 50% distribution, but in reality it needs to be inflated. So 110 divided by 0.5102 goes up to 215. So this would be the new values that we will have for actual data that would be there. And in this case, we are going to bring this down because we had artificially increased the number of actual ones 25 times more. So now we want to bring that down by 25 times. So 80 divided by 25 and 420 divided by 25 gives us these numbers. So now we have a new confusion matrix which has these values: 764.4, 3.2, 215.6 and 16.8. And that would be the way we will be using to determine how well this model has done. What is the total accuracy levels of this model. So that's something which is important, oftentimes necessary to do in most of the models that we will have. In many of the contexts that you'll see, you'll always have this situation where there are certain classes that are more important, but they're also rare in the data set. So we have to do something about it. Now we can adjust, before we go there, we can also adjust the lift curve for oversampling because lift curve, it's going to be more useful measure in low response situations, especially when we are not so much interested in just classifying all records correctly, like we just did in this previous example, but we want to find a model that guides us towards which records are more likely to contain the response of interest. So the top 10th percentile, 20th percentile, like we just talked about, that become more important. So we have to adjust the lift curve also for oversampling. And the way we do this is basically the same approach, the weighting approach that we just saw here. We sort the validation records in order of the predicted probability of success, which we saw in one of the examples, that we look at the probabilities and then decide what exactly the prediction was and what the actual was. And for each record, then we record the cost associated with the actual outcome, but divide that value by the oversampling rate. In our previous example, the oversampling was 25 factor, so we divide by 25. And then the highest probability record, the value above is the y coordinate of the first point, and the x coordinate is the index number of 1. So this is very similar to what we just did, except for this one step, which is the oversampling rate has to be considered in the case of oversampling that we did in the model. So with that, I think I'm going to pause and see if there is any questions or clarifications that needs to be addressed for performance evaluation of models. Not seeing any questions. I'm moving on to the case study, and I'm looking forward to a discussion on this, because this is essentially using all this, what we talked about, a lot of the concept that we just talked about in this case study on StreamMax. So this is another case that we had for today. It's a mid-sized streaming service, independent films, international content, and classic cinema, with 4.2 million subscribers. Now they have a monthly churn that has increased from 2.8% to 4.1% over the past year. And this costs them money, $1.8 million annually in lost revenue. They want to do something about it. Now, current intervention program that they have for retaining these people costs them $12 per subscriber. Right? They do personalized content recommendations, temporary discount offers, etc. And that is where the cost goes, $12. And by spending that amount, they're able to successfully retain 35% of their at-risk subscribers. So they spend money, but they are able to get these 35% of at-risk subscribers and retain them. But it's expensive to execute because we have such a large database, 4.2 million subscribers. We cannot send this $12 for every one of them. So we have to decide which ones to send to. So we have to recommend an appropriate machine learning model that can help with the situation. And we have a budget of 2.4 million for retaining customers. Right? So that's the problem in this particular context. And the case already tells us that they're evaluating three models. One is a logistic regression model, which we will talk about later. So right now, the question is less about what the model does. It's more about looking at the confusion matrix and other performance metrics we talked about and determining what might be the right approach here. So the team has developed these three. And these are all trained on 18 months of historical data with 52 different predictors. Right? So a lot of predictors. This could include viewing behavior, their account tenure, payment history, etc. And we are trying to capture the churns. The models were evaluated on a validation set of 84,000 subscribers, which is about 2% of the customer base. With that, we are able to get this sort of confusion matrix that we see here. Now, if I look at this confusion matrix, we already know how to capture the performance, accuracy, for example, accuracy, sensitivity, specificity. We talked about all of that. There's a formula for each of them. So we can actually convert this confusion matrix into its corresponding performance metrics like this, again, provided in the case study. Now, based on the confusion matrix, which model should we recommend becomes complicated because the confusion matrix has so many different types of metrics. Matrix could be viewed from accuracy perspective or error rate, sensitivity. So not everything is great in one single model. Some models are good in one versus the other. So I'd like to open it up here to see what were your thoughts when you read this case and how did you go about thinking about this. All right, looking for some discussion here.
Based off of my understanding, I thought Model A was better because of the overall accuracy.
Okay, yeah, so the accuracy is the highest here. So that would be one metric one could choose. Although we saw some examples where we saw accuracy may sometimes be misleading, right? So we have to keep that in mind. What other thoughts come in mind? Others?
I don't think there actually is one that is like the optimal choice necessarily. It's more like a trade-off in a sense, because like if you look at the predicted churners, Model C is more than twice as many predicted churners than Model A. So there's definitely going to be many false positives as well, and we are on a budget. So yeah, I don't think from all these three models there's an optimal choice necessarily.
Okay. But if you were given this information, then how would you go about thinking about this? I mean, obviously one is accuracy, just look at that and say, okay, which one is most accurate? But others could be like sensitivity. Clearly this is highly accurate, but highly sensitive, very low on sensitivity, right?
Yes.
So would you choose a different metric than what Ali had chosen?
I mean, I would probably go, if I had to choose one of these three models, I would probably go with Model B.
Model B, okay, why?
Because it is right in the middle. It has not too many predicted churners, and the sensitivity is better than in Model A. I mean, the sensitivity is overall best in Model C, but then again, it predicts 6,400, and the company I think can't afford
Okay.
to pay like the retention efforts for 6,400 customers.
All right. Right. Okay. That's one way to think about it.
I was gonna actually change mine too, because what I remembered was that I think Model C flagged about, I think it was like 4,000 maybe subscribers who actually stay. So and the company actually ended up losing money from the case. So I was also gonna go with Model B after recalling that.
Okay. So therefore, cost becomes an important factor in both of your thoughts here. Okay. So we'll take a look at this here. So we have to obviously decide who should be viewed as churner versus non-churner. How do we decide that? We decide that based on probability cutoffs, like we talked about, and all these metrics that we just talked about was based on 0.5. But what happens when we change that cutoff? Right? That's one question which will come into mind. What if I don't use the default 0.5, but change it from 0.3 to 0.7? And there are ways in which we can look at even larger range. We have a program, Python program, which has been provided to you, which shows you how you can look at across multiple probability cutoffs. So what if I had a lot of these distributions? I can look at all these different models. Right now it's only one of the models for which we are looking at the cutoffs and how the accuracy will change over time so this one is only for Model B, because Model B had 95.9% overall accuracy for a 0.5 cutoff. That's what you see here also. But if you change it, then it changes the accuracy. Sensitivity will go up. So the question here is, which cutoff would you, I mean, let's take Model B here. Given the context that we have here, what would be your choice? Like, would you want to go lower than 0.5? Would you want to go higher than 0.5 for your cutoff? Right? Anyone? Okay, let's see. Last question. I'll probably call out now. Rochelle, maybe you can tell what you think. Sairaj? Yeah, we cannot hear you. I see you have unmuted, but yeah.
Hello.
Yeah.
Hi, Professor. So, in my perspective, I think we can use the cutoff uh, between the 4,000 to 5,000 predicted channels for the model people.
So the cutoff you would choose will be less than 0.5, greater than 0.5?
For model B, like I wouldn't use the default 0.5 cutoff.
You would or
So,
you would not, you
y-
said?
yeah. So, as I stated yesterday, I've gone through the case study. So, I would probably sort the customers by the churning probability and uh, choose the choose the cutoff that is around the 4,200 customers. Uh, because this fits the budget and cost and gives a good balance between the churners and controlling the false positive.
Okay. So which among these, which one would you choose then among these cutoffs?
Sorry.
Among the 0.3, 0.4, 0.5, 0.6, and 0.7, like we have all these, right? 0.5 was the default.
Yeah.
So you mentioned something like 4,500 or something like that, but I was curious to see what you think about the cutoff point. Which one would you go lower than 0.5 or higher than 0.5? Because going higher would have some
Yeah.
implication, going lower will also have some implication, right? Like
Uh,
we just talked about that.
yeah, we just discussed.
So would you go lower or higher?
Uh, According to my assumptions, I feel we uh, can go lower than the 0.5. Uh,
Okay. All right. Any other thoughts? I mean, the interesting thing about case studies is that one can reason both ways, right? I mean, one has to just understand what could be the implication of one way, but the choice is again business context dependent. So in this case, if you go at zero point 0.7, you are now considering many of them as churners, costs more. 0.3, you will be more strict here and losing out some churners. So this is a balance that one has to account for. And that's something which is a business question. So there this case then brings up the question of ROI. Like some of you had also talked about the cost involved and the revenue that you will gain. And I mentioned earlier in our discussion that the way we capture ROI is through determining the gains chart and rank orders, not just looking at classification, but also looking at it in terms of the lift that we get from our model. Right. So this is what this. Yeah. Go ahead. You have a question here. I see.
Yeah. I wanted to ask again for the cutoff point.
Yeah.
If we had some, it would be relatively easy to model the perfect like cutoff point if we had some measure of okay, how long do customers who are about to churn stay once they receive the offer?
Hmm.
So how much like lifetime earnings would we get from them, or what return on investment would we get from them discounted to today, right? That should be the perfect way of identifying the right cutoff point, no?
Yeah. So the case provides us the information as $340 of the lifetime value of subscriber. They give us $340 lifetime because they keep the subscription for certain number of months and they pay us a certain amount of money every month, $14 I think. So $340 is what the case provides us as the, and it's true that we would want to look at the cutoff in light of the ROI, in light of what the subscriber value is in terms of the revenue, but also the cost of intervention. Cost of intervention is $12, right? So both will play a role. And that's why something like a lift chart becomes very important, because we want to rank order these customers to decide which one to target, which ones we should focus on. If we had limited budget, we want to choose the top 10% based on the probability, top 20% based on the probability. Which one should we choose? So that's what this is doing. And these are the three models. And what we see in these three models, besides what we earlier saw in our performance metrics like we had here, the previous discussion was about the performance metrics of the three models in terms of accuracy, error rate, sensitivity, etc. But here what we're doing is the same three models now are evaluated based on lift chart of what is the lift that we get. And we talked about what that lift means, how much more than the random selection we gain by choosing model A versus model B versus model C. And here we can see that model B ends up giving us a higher lift of 5.2x for choosing the top 10%. Even when we choose the top 20%, it's still the highest, 4.1%. When we choose the top 30%, then Model C becomes slightly better, and so on and so forth. So if we had limited budget and we can only approach the top 20% of our predicted customers, churners, then this would be our early hint that maybe it can be a Model B because of this reason, right? Because of the 5.2x benefit that we get compared to 4.8 versus 4.6. So this is one way to capture the ROI or look at the ROI, but the other way is to explicitly calculate it. They actually do the math and understand what's the value of choosing Model A versus Model B versus Model C. Now, having seen the previous slide, because Model B has a better lift scores here, suppose I choose Model B, but I consider the value, subscribers lifetime value of $340, cost per intervention of $12, and the fact that an intervention may not be successful only 35% of the time it's successful. And we have a monthly budget of 200,000, which means that we can only intervene for 16,700 of them. We can do this calculation for all the models, right? So it's just one of the model which has been shown in the case, Model B. What happens when we are using Model B at a 0.5 cutoff? Then this is what the number of subscribers who will be flagged. We already saw that number, 4,200 subscribers. Now, among them, 2,100 are true churners, suppose, and then in that, because we now can calculate that value here, so we will use 35% success rate that they would save a certain amount of money because of that intervention with only the top 10% or top X percentage of customers. So with a 35% success rate, they would save these many subscribers and then this much of lifetime value from those subscribers, right? So that's basically the total lifetime value, but there's a cost of reaching out to 4,200 of them at the rate of $12. So the difference between these two will be what the total value, net value is. Now this net value calculation we can do for Model A and Model C at 0.5 cutoff, where they have different subscribers who will be flagged. And then we can understand which one gives you the best net value. So that would be the ideal scenario that we would go through. While we can stop here in the previous slide and say that, okay, I'll go with the lift, but ideally speaking, companies should go one step further and capture the net value for each model based on the revenue and the costs involved, and then determine which one they should choose. Right. So that's something which is the process that we learned from this case study. So the objective of this case was to highlight the fact that oftentimes there will be competing models, and it's quite attractive to just go with accuracy and quickly choose that, but there is quite a few more steps to undertake before we decide which model because of the context in which you are in. If you're working in a hospital, healthcare context, very different scenario. Sales promotion, very different scenario. And we didn't even talk about the rare cases right now. What happens, there are rare cases and all those things. But if that is the case, we have to oversample, and other things also need to be considered. So that's your performance evaluation discussion with the case studies. We've talked about this, so hopefully you have good understanding of how do you evaluate performance and how do you decide which model to choose, what are the steps that you should take. Now, one of the very popular models that companies use for prediction is multiple linear regression. Now, you must have all studied multiple linear regression or linear regression at some time in your statistics classes, right? So this is essentially the same model, except that we are using it for prediction rather than just explaining something. We talked about the difference between a statistical model versus a predictive model. So this is a mathematical translator, basically connecting your inputs to outputs. Inputs are all these x1s, x2, x3, all these variables that can result in some outcome. Right, so real applications could be sales revenue, it could be the price of a smart TV, like our example case that we have in the readings, credit card activity prediction, etc. And y would be that outcome, but X will be all those factors, all the predictors that can result in it. And then there's the error term here, E, which is things that we cannot explain. So it's a simple model, versatile enough for different contexts. So we'll be using this as our starting point and then build on this with different models. So I already talked about this, that regression can serve two purposes: understanding why, which is the statistics side of things, where we can look at the coefficient, beta coefficient. After running, we get beta coefficient for all the variables and determine how much impact that is. But what happens next is our prediction. In this case, we will be using training set and validation set and predicting based on the learning that we have done from the training set. Right, so this is where most of our focus will be. And oftentimes we'll see that a model that is great in explaining may not necessarily be the best for prediction. So we have to be careful about our objectives and use the models appropriately. Now, what are the key differences? Obviously, here we are only interested in understanding relationships. So beta coefficient, significant or not, how strongly it's going to impact Y, the price of the product or sales revenue or whatever. Here we want to actually accurately predict for a new data set we have not seen yet. Here all data is used to estimate. Here we split the data. Here goodness of fit, R square, etc. becomes important. Beta coefficient becomes important. In this case, we want to understand the predictive accuracy on new data, the validation data, how it works. And we look at the predictions for the new data set. Right? So that's sort of the big difference between explanatory models and predictive models. Now, this underlying sort of mathematics behind this linear regression model is the ordinary least squares. What this engine under the hood does is it finds the line that makes prediction as close to the actual value as possible. So if all the data is put in a scatter plot, X and Y, and a lot of data point, it tries to create the best possible ordinary least square line that can pass through these dots, so that the distance between that line and each of these points in your data is the least, the square of that distance, right? So it tries to find that particular line. And the good news is that even when assumptions wobble, we have some assumptions within which we operate this. But even when these assumptions are not in line with what we had thought of, they typically tend remarkably well. The OLS model is still a decent model for it. So we don't need to lose sleep over predicting perfect residual distributions. What we want to work on here is more of prediction for tomorrow. So we are not concerned as much about the level of explanation that it can provide, but more about the predictive capability. So this is the case that we have in our reading, which is being used throughout and has been discussed. So there's a video which covers this entire Python program that we are using, and it's been uploaded on your Canvas. So you can take a look at that. But it's predicting smart TV prices. A consumer electronics retailer offers trade-in programs, let's say for premium smart TVs, and they need to accurately predict resale prices. So the challenge here would be that we need to ensure trade-in and resale programs remain profitable, and therefore we want to predict the price that each used TV can fetch us. And that will require using a rich data set, which includes the screen size, it includes the age of usage of the product, number of hours that it has been used, how many smart features it has, what power source it is running on, etc. Now, we will have a range of prices for these products. We will use training set, which comprises of 60% of the data, and 40% will be used for validation. Right? So that's what we have done in this reading to understand how it works. Now, the model coefficients, once you run this, will tell us what drives the smart TV resale prices, which ones have higher impact on the smart TV resale prices compared to other factors. So power source happens to be a categorical variable. Now, it has three categories: battery, hybrid, and wired. So battery becomes the reference category, and the other two are the categories that we are predicting the price on as compared to the battery. So these are the coefficients which you will get when you run the model, and age reduces the price, whereas others increase the price for resale as one of the variables. So these coefficients are helpful in ensuring that our data actually makes sense. What we are seeing here makes sense from practical understanding of this context. And this is something which, again, has been something which we have done in the Python model in the video to show you how it works. Now, when we run this, we also get the metrics that we just talked about, the performance measures. So RMSE is $664. Mean absolute error is $536. So these are values that tell us how much on average we get error from what exactly the actual price might be. Right. So by looking at this, we can see hybrid adds the most for the value of the item, and something which reduces this, and the dummy factors. So it's a sort of straightforward explanation of what we have done until now. Now, how good is the model? Obviously, multiple metrics are there. RMSE of 659 will tell us that a typical prediction error is about $660. A typical prediction will be off by $660 in some sense. With TVs that range between 1,000 to 8,000, that's about 10 to 15% error that we expect from this, right? Which is what we also see in mean absolute percentage error. It's about 11.52%. Right? This confirms that the errors are around that range. Now, whether it's good or bad, that depends on our profit margins. Having 11.52% error, does it impact our profitability quite adversely? In which case, we'll have to think about it. So that's something which is a concern that we will view in light of what the value of that is. Most errors fall within plus or minus $2,000 in the data set when we see that. And for business decisions, we typically need to weigh the prediction error against the cost of being wrong. Right? So that error that we see versus cost of being wrong, which is how much we'll lose because of that, comparison of that trade-off is important. Now, this entire discussion is not about just running the multiple linear regression model, which obviously is an important one, but we also want to understand which variables to choose. And something connected to the principal component analysis talk that we were having earlier from the case study. A kitchen sink problem would be, why don't we just put all the variables that we have in the data set? It's very tempting to do this. Right? With this fast computers that we have, why should we even bother selecting the variables? Now, in several instances, actually, it's expensive to collect many of these variables. So what would happen is that more variables we add, sometimes we'll end up having more missing values because some of these variables could have more missing values compared to the other. And sometimes parsimony actually can be beneficial for insight. If you have adding so many variables, we won't know what exactly matters. But if we are more parsimonious, then we get better insight of which variable we should focus on. So that's another reason why we want to reduce the number of variables. And there's another reason, which is multicollinearity, a very important factor, which is if I have 5 variables and I included all of them to predict price, for example, sometimes some of these 5 variables will be correlated with each other. And if we include and very highly correlated with each other, being correlated is okay, but if they are very highly correlated with each other and we include both of them in the model, it creates what we call a multicollinearity problem. And that makes the coefficients unstable and we cannot trust what we get as a result. Right? So that's something which also becomes important, that we are not messing up with our model's results. So we don't want to include all the variables. Now, this brings us to the fundamental tension that we have in predictive modeling, and that is when we have too few predictors, then it creates high bias because we are underfitting the model, right? We have less variables, so we are having higher bias and we are underfitting the model. On the other hand, if we have too many variables, then we have high variance. We are overfitting the model. We don't want either of them. We want to be somewhere in the sweet spot, not underfitting, not overfitting. Accepting some bias sometimes can reduce overall prediction error by cutting variance, and that's the essence of our trade-off that we want to capture here. Now the question is, how do we reduce predictors? Principal component analysis, what we saw earlier, can have some advantage, but also has a disadvantage that sometimes these variables are not easy to interpret. But there are other mechanisms that we can adopt. One is you go through the domain knowledge, right? So if you're working in this industry, we can always understand which predators actually matter more, and we need to keep them into consideration. So that's one thing. We can consider collection costs, correlations, missing values. All these things can play an important role in determining which variable to keep and which one not. So those are all domain related. And then computationally, we can also look at different ways in which we can do this. And that's something which we will want to learn in data mining course that we have here. What are some computational methods that can help us determine which variables to keep? So we can use some algorithms. And these are, for example, exhaustive search, stepwise algorithms, backward elimination, regularization. There are different types of techniques that we have explained in this lecture, this reading, and also in the Python program. And in each of these methods, we use some metrics like adjusted R-square. Now, adjusted R-square is different from R-squared in the sense that R-square simply tells us how much explanation of Y variable we get from the X variables. But what adjusted R-square does is it reduces that R-square with every additional variable if that variable is not useful. So if you keep on adding variables, sometimes that R-square value starts to decrease. And that is what is captured in the adjusted R-square value. And that's something which helps us determine when adding that variable actually is not beneficial for us. Right? So the best model will combine typically the domain expertise and statistical rigor. We will combine the two. And that's when we actually are doing the best here. So we'll go over each of these, and the technical side of this and the Python program side of this has already been done, and you can take a look at that as well in the reading as well as the video. But exhaustive search, what this one does is it looks at all subsets of variables, right? So if we have 5 variables, there can be 2 raised to the power 5 different subsets we can have. So it creates all possible combinations, run all the models with these combinations, and then select which one results in the best metric. And the metric are the adjusted R-square, AIC, which stands for Akaike Information Criteria, and BIC, which stands for Bayesian Information Criteria. So there are these metrics that it uses. It looks whether adjusted R-square has gone up in a certain model. That would be a good model. And has the AIC and BIC gone down? Because lower AIC and BIC is better. Indicates that it's a better model. So we look at those models which have high adjusted R-square and low AIC and BIC and choose that subset of models. Right? So that's something which is what we do. So it's a good approach. The only challenge is that it is not practical when we have large independent variables, large number of predictors. In many practical scenarios, we will have as many as 52 different variables, like our case study had 52 variables, and doing all possible combinations, it shoots up exponentially. So it becomes quite expensive. So what we, in the case of exhaustive search for smart TV example that we have in the Python program, we go through the process and we identify the best combination results in the highest adjusted R-square is, because after that adding more does not help us, include 8 variables. These are the 8 ones. So it peaks at 8 predictors. Adding more does not help. Lesser than that has less adjusted R-square. So that was our best model. It also has the lowest AIC. You'll see that in the Python results as well and in the readings. But because it has some issues with that exhaustive search having so much of computational requirement, we also have other approaches when exhaustive becomes not impractical. And these are iterative search methods like forward selection, backward elimination, and stepwise regression. Right? These are 3 different ways in which we can do iterative search. Now, forward selection is when we start with no predictors in the model. We just have a constant. So in regression, there's a constant, all the predictor variables, and there's an error term. So what we do is we start with no predictors and then add one variable at a time. And we choose that variable which has the largest R-square contribution to the model. Right? So this is where we basically add one at a time and then see which one adds to the R-square the most. That's the most important. And then keep doing this. Now it's great from the point of view of not having to use the entire exhaustive search. But the disadvantage of this is that sometimes pairs of variables can work together for the model as compared to being considered alone, right? So pair of model, for example, high income family and well-educated sort of background of the family, both combined together can predict something as an outcome better than high income by itself. So that's sometimes necessary to include both of these variables at the same time together, and that's something which forward selection cannot do because we are doing one variable at a time. So that's a drawback. We have to be aware of that. Backward elimination is exactly the opposite of forward selection. What we do here is we start with all the predictors and then we drop one at a time. We remove the least useful, which actually does not add anything to the R squared. So we remove that. And the weakness here would be that when we are using that initial model, when all the predictors are put in, the results that we get can be unstable because of like the multicollinearity problem that I mentioned earlier, right? So that's something which can become a problem here in backward elimination, which we need to be aware of. The third one is stepwise regression, which basically is like forward, but also considers dropping non-significant predictors at each step. This is more conservative. So it's essentially trying to do both forward and sort of eliminating some of the variables when not needed. It combines both. It's more conservative and selects fewer variables typically, but none of these models are perfect, right? We can never have a perfect model. Again, nothing can guarantee that this is going to give us the best subset. It is an iterative process. It's a learning process for a data mining analyst. They will have to go through these models, look at the results, and then look at the domain and decide which one is the best based on all that composite understanding. So here the forward selection in action, I think the text is a little less to be seen here, but essentially these are what was added in each step, right? So in the first step, you add the power source hybrid, and I'll change this to a black color so that it can be seen. So power source hybrid is added in step 1. So we see AIC was 40,185. Then it goes down, AIC goes down to 39,000, which means the model is becoming better by adding another variable, which is power, age, month, and so on and so forth. So we keep doing this until step 8. There are 8 predictors that are selected. It's the same 8 predictors that were also selected in exhaustive search. So we can also look at the RMSC, etc. So it basically arrives at the same model as the exhaustive search. So that's a good sign. In some way, 2 models converging is a good sign. Now, those are different techniques for variable selection that we just talked about. There's another way to do this variable selection, which is called regularization. What we do in regularization is not that we choose all the variables exhaustively or select forward and backward elimination, etc. But this is a more flexible alternative. Instead of setting the coefficients to exactly 0, what we do is it shrinks each coefficient of the variable towards 0 when it's not useful. So highly correlated predictors will cause unstable coefficients, and what it will do is highly correlated predictors which cause coefficients with high standard errors. These were the ones that will be first to be eliminated, and then they'll constrain some of this combined magnitude of coefficients so that the variance is reduced and the predictive power is increased. So that regularization can also come in multiple forms, and it in the end tries to get to a subset of variables where those variables coefficient did not shrink close to 0. All the others did. So whichever survived that are the ones that we will keep, and the ones that got shrunk to 0 are the ones we eliminate. Now, for any regularization that we will do, we'll always have to normalize the data before we run regularization. So we don't have to do that with what we just talked about in forward selection and all those things. But in this case, regularization, it always is necessary to normalize the data before doing any of these regularized regression. And there are, at a high level, 2 types of regularized regression. One is called ridge and the other is called lasso. And there are 2 variants of ridge and lasso, which we'll talk about. So Ridge basically uses L2 penalty, which is sum of squared coefficients. So basically it shrinks everything but never to zero, because squares don't shrink to zero. It tries to shrink closer to zero but never exactly equal to zero. And all predictors remain in the model because nothing is going exactly equal to zero. Lasso, on the other hand, uses L1 penalty. So this L2 and L1 penalty is sort of a technical term, essentially trying to mention that L2 basically means the squared of this term coefficients is used as a penalty. And this is basically saying you don't take a square, but the absolute value, L1, absolute value of the coefficient, and use that to shrink. But in this case, it shrinks and can make some of these coefficients go to zero. Right? This one does not, but this can. And then it does automatic variable selection, and it creates more of a sparse model because in this, some of these variables will drop out. When you need a sparse model, you will choose Lasso. When you want to keep all the predictors but dampen the effect of these other variables that are not that important, then you use the Ridge type of regression. Once again, in the data set, we have the smart TV. We have actually gone through the two types of Lasso. As I said, Lasso can come in different variants. One is the Lasso, general Lasso, where there's a coefficient called alpha we have to specify, alpha equals 1, which is used here. And the other is called Lasso CV, which is using cross-validated data, which does not require us to specify alpha. It automatically determines which is the right alpha. And similarly, in Ridge, there are two variants. One is Ridge, where alpha is determined. In this case, we are using it as 1. And Bayesian Ridge, where alpha is automatically detected. So we run all these types of regularization models, again, in the reading and Python program video. You'll see that we have this regularization also covered. For each of them, we can then determine what the RMSE is and compare it with the ordinary least square. We can compare all the other error metrics, how many predictors were included in this, and this way we understand, which model will be the right model for us based on the error metrics and everything else. So that's sort of something which we have seen. Now here we don't see too much of advantage with regularization. Regularization is not excelling too much compared to just an OLS, very close results here. And that's because regularization typically excels when you have too many variables, like 50 plus predictors. When you have so many different variables, then when you use regularization, and that's typically the case in business situations, then actually you'll see that there will be a big difference in these error rates, and it helps show the power of regularization in those cases. So just to summarize here, regularization shines when there are many predictors compared to the relative to n, and there's high correlation among these predictors. Some predictors are highly correlated with each other. There are unstable coefficient estimates, and there can be risk of overfitting. When all these conditions are there, then regularization is very helpful. And now within regularization, you use Lasso when you want automatic variable selection, and Ridge when you want all the predictors that can contribute. Right, so that's sort of the two things, and we have Python tools that can help us do this. And within each of them, we already talked about two variants that can come, Lasso and Lasso CV. CV is basically cross-validation version, and Ridge and Bayesian Ridge. So the real world application for these kinds of things would be, for example, credit card spending prediction, a bank predicting monthly credit card spending. And predictors could include income, age, tenure, past spending of the customer, payment history of the customer, and many more. Now the model can achieve, let's say, 15% lift, which we could always do with what we have learned so far, in cross-sell conversion. So in another study, we could, for example, see that customers who bought anti-scuff chair leg protectors, completely unrelated products, typically will have lower credit risk. Sometimes we'll see some hidden relationships between variables when you have all these different types of variables. So those are unexpected predictors that we want to sometimes include in the model, which we would not have included by default, because that's doesn't. So these hidden relationships can be something which we can sometimes unravel with the help of these models that we had considered, including the regularization type of models. So that's sort of our overall predictive modeling workflow that we will follow. We train and we split the data, like we talked about, training set and validation set. We fit the model on the training set. Then we select the variables appropriately. So we could use all these different approaches to reduce the predictors. And then we validate the model on holdout, the test data. So that's something which and there are different ways in which you can split the data, but typically 60%, 40%, that's what we're using in our reading also, and all the Python program, but we could also use 70, 30, 80, 20. There are different approaches for this. Now, some common pitfalls, overfitting is one, we want to avoid that. Model memorizing training data but fails on the validation data, we don't want that. Data leakage, we want to avoid that, which is using validation data during training. So they have to be clearly separated out, the two data sets. Ignoring multicollinearity, when there are highly correlated variables together being added, it can create unstable coefficients. We don't want that either. And kitchen sink approach is obviously not helpful. When everything is put in, it can create multicollinearity by definition. Forgetting to standardize, especially with regularization, we do want to standardize first before we run regularization. So this is important first step. And chasing R squared is not helpful because we are not trying to explain models. It's helpful when we are doing explanation, but in our case, it's about prediction. So what's more important is validation performance, how the RMSE, MAE, all the performance metrics that we talked about fare in the validation data set. So this is the last slide that I have, and with that we'll conclude. A decision framework would be for the variable selection is that when you have few predictors, when number of predictors are less than 15, go with exhaustive search, because you can always go through all those models and it still can be easily computationally managed. And look at adjusted R-square and AIC to select the best model. If you have many predictors, 15 to 50, then go with stepwise. It could be forward or backward or a combination of the two. Or any of the three iterative methods, right? These are faster. But the challenge is some of the good combinations that you may have gotten through exhaustive search can get missed out. And if you have a lot of predictors which are beyond 50, then you choose regularization, lasso or ridge, depending on whether you want all the variables or you want to eliminate some of them. So it also handles high correlation among these variables. You can use CV for tuning. So that's sort of the way in which we will think about variable selection, depending on the number of variables. Now, always we should start with the domain knowledge, because no algorithm that we have talked about can ever replace understanding the data which we learned from pre-processing and everything else we talked about earlier. So it's always important to do that, understand the domain and understand the data very well before we run all this. With that, I think I'd conclude. We've covered the exhaustive, we have covered the multiple linear regression as well as data evaluation today with the two case studies. But I'll take any questions you have. Right, seeing no questions, I'm going to respond on the idea that you have submitted for your project soon, and then any changes that I think you need to incorporate. And after that, you can start working on it. All right, thank you. Have a good rest of your week and see you next week.